Welcome to the channel. The problem is given on the MOSFET and we have to find out in which region the MOSFET is operating. Here the current drive strength K, threshold voltage VTH and W by L ratio is given, and we have to find out in which region the MOSFET is operating. So first of all, let's see the MOSFET. So this is the MOSFET as I am considering NPN MOSFET. I am drawing the rough structures to understand the concept of MOSFET. So this is NPN type, substrate is P. This is insulating material SiO2. This is polysilicon. The gate terminal. These are the metal contacts for the source. And drain. And one more terminal. That is nothing but the body terminal. So in NPN type MOSFET, we are connecting it to the ground. Now see what happens. Initially MOSFET is in off state, which means that VG is nothing but the gate voltage, and VDS is nothing but the voltage which is applied between the terminals drain and source. So we have to consider first of all these two voltages, 1 volt VG which is applied at the gate terminal, and VDS, that is the voltage between drain and source terminal. So if VGS, we can consider VGS or VG voltage. VGS nothing but the voltage between the gate and source terminal, so that is nothing but the VG minus VS. So if you are considering the VS also at ground, and we are considering some voltage here to the drain terminal, and we are considering the voltage here at the gate terminal. So VG is the voltage. We can call it as VG only because VS is 0. Which is nothing but the VG voltage only. So if VG voltage is 0 or more negative, you can consider, then MOSFET is in off state, and this region is nothing but the cutoff region. Now we have to apply some gate voltage. We have to increase the gate voltage starting from 0 and go on increasing the voltage. So if you are going to increase the gate voltage, what happens here? This is P type of materials, which means that the holes are majority carriers, and this is N type of material, which means that the electrons are majority carriers. This is N type material, which means that the electrons are majority carriers. In the previous some videos, I explained the PN junction diode recombination, holes and electrons, and how is the movement of holes and electrons. I am providing the links in the description box to watch the videos related to the PN junction diode and holes and electrons, and how the combination will be there, depletion region will be there. So what happens in this case? If you are starting to increase the gate voltage, here the holes are majority carriers, and if you are applying the positive voltage, then the holes are repelled at this side and they are forced or pushed to the downside, and here the channel will be created, which means that if you are applying some positive voltage, the holes are repelled towards the downside and will create some space to flow the electrons from source to drain. How these electrons will flow from source to drain? If you are applying small positive drain voltage. So the voltage at which the channel is formed, I mean to say the gate voltage at which this channel is formed by pushing all holes towards the downside, That voltage is nothing but the threshold voltage. And at this threshold voltage, the MOSFET will be in on state. MOSFET will start the conduction of the current, but not maximum. It will start the current to flow. So this is about what the threshold voltage at which the channel is formed. The gate voltage at which the channel is formed is nothing but the threshold voltage. And if you are applying the small drain voltage, then the electrons will be starting moving from source to the drain. Because these regions are n-type, means electrons are majority carriers. And here if you are applying small positive voltage, then all electrons from the source will be attracted towards the drain side, and there will be a conduction of current. But this will be a small conduction of current. So here in this region, if you are starting to increase the threshold voltage, I mean to say the gate voltage, which is at the threshold voltage where the MOSFET start to conduct. So this threshold voltage, if you are going the gate voltage to increase above the threshold voltage, and there will be some drain voltage at particular drain voltage, I mean to say drain source voltage, then here this region of operation is nothing but the linear region. Here the linear relation between the current and voltage. So if you are going to increase the voltage, drain voltage, the current will also start to increase, and this region is nothing but the linear region at certain VDS point. At particular point, the VG is fixed now, and if you are going to increase the VDS voltage, I mean to say VD voltage, from small value to the maximum value, or we can say at a certain point, here the maximum current will flow, that is nothing but the drain current. So after a certain point, or at certain VDS, I mean to say till the certain value of VDS, MOSFET will operate in the saturation region, and above the certain VDS, above certain drain voltage, if you are going to increase the VDS voltage above certain limit, then what happens here, again the holes from the P side, this voltage is more positive and more electrons will be attracted towards the drain terminal, and this is P type, then again holes will be attracted towards this negative side, and there will be a recombination of holes and electrons at the drain side, as we are going to increase the drain voltage above certain limit, and there will be a recombination of holes and electrons again, and this will reduce the length of channel because of the recombination of the holes and electrons at the drain side, because there will be a higher electric potential at the drain side because of this positive terminal, and more electrons will be flowing from source to the drain. So more and more electrons at the drain, so holes will be attracted again towards the drain side after certain voltage of VDS or VD voltage, and there will be a recombination of holes and electrons which will reduce the channel length, and this effect is nothing but the channel length modulation. Now we are going to keep VG constant, and VDS is sufficiently high voltage, then we are getting constant ID current. Say this is VG1. If you are going to increase VG1 to VG2, and we are keeping high VDS at certain value, then ID will increase. Say this is ID1, say this is ID2, and we are getting the constant ID2 value. So if you are going to increase the voltage, gate voltage, the drain current will increase. But if you are going to fix the gate voltage for high VDS value, we are getting constant drain current, and this region is nothing but the saturation region. This region is nothing but the saturation region. Now see the important conditions to operate the MOSFET in various regions. So here VG voltage is 0. The region is cutoff region. If VDS is small, or which is less than VGS minus VTH, then this region is linear region. And third condition, if VDS is greater than VGS minus VTH. So VTH is nothing but the threshold voltage, VGS is nothing but the voltage applied across the gate and source terminal. Then the MOSFET will be in saturation region. MOSFET will be in saturation region, and this is about NPN type of transistors. All the conditions that I have given for the NPN type of transistors. So we have to find out the condition in which region this MOSFET is operating. So we need to calculate the VDS voltage and VGS minus VTH voltage. Obviously, the MOSFET will be not in cutoff region because VTH is given 0.5 volt and gate voltage is given in this problem, that is 1.2 volt. So obviously, MOSFET is operating in either linear region or saturation region, but we have to find out the VDS voltage is less than or greater than linear region or saturation region respectively. Solution.